Okay, so we're going to go over limits and continuity today and some rules for differentiation. Since we're going into limits, I'm going to start with this problem I talked about last time. Said you could possibly work that at home, and then I'll work it out in class today because it kind of brings us into limits. We have a test Wednesday of next week. Look on the syllabus. I'll say some more about that at the end of class. It's going to be primarily Scantron. But again, I'll talk about that towards the end of class, and I'll also send out an email too. Okay? So, like I said, what we're going to do today is we're going to talk about limits. We're going to talk about continuity, and we're going to talk about rules of differentiation. So, this was This was a problem that I spoke about last time, and this problem over here, I said try that at home, and it's you want to find the derivative of the function at -1, and the function is f of x is equal to -x squared plus 2. Can anyone tell me what this derivative should be, what they think it should be? Minus 2x, and if I plug in -1, I get -2, okay? That's because one of the things we're going to learn today is that we can split derivatives over addition. We have a constant term and we have a -x squared, so we can just take them separately. But we're going to see that, but you're right, the derivative is -2x. But how do we do that using the definition of the derivative? So here's the problem. If you worked it out at home, you can try and follow along. If not, you can just watch the board. And remember, what we want to do is we want to find f of x plus h minus f of x divided by h. And then what we're going to do is after we solve this, remember it says let h go to 0, and that's the derivative. Well, we're going to talk about letting h go to 0, and we're going to talk about what this means more, but we have an idea of what it means already. That means the limit as h goes to 0. Okay? So that's how we're going to denote it. We're going to talk more about that. Yes? I'll turn. Okay, so we wind up with this over here. Remember we said we let h go to 0, and that gives us the derivative. And sometimes it just means let h equals 0. It's intuitive. Other times it won't be that simple, but how we're going to talk about that in the next section is going to be, we're going to write the limit as h goes to 0, okay? That's how we're going to communicate to the reader to let h go to 0. So for this problem, we know that x is equal to -1. So what we're going to do is f of 1 plus h is going to be equal to, well, this says square whatever parentheses, multiply -1 and add 2. So I'm going to square what's in parentheses. 1 plus h is in parentheses, I'm going to square it. Multiply it by -1 and add 2. Right? So f of x is equal to this. It says take whatever's in the parentheses here, square it, multiply by -1, then add 2. So 1 plus h is in parentheses, I square it, multiply by -1, add 2. Okay? And if I simplify this, if I FOIL this term, it's going to be -1 minus 2h minus h squared plus 2. Okay? Now, the other term I want is just f of, I want f of x, but f is this over here, and x is -1. So, let's see. Oops, I put a 1 here. It should have been a -1. Right? So x is equal to -1, not 1. So this should be a -1. So this is going to be a minus here, and this is going to be a plus here. Okay. So let me see. It's going to be okay. Yeah, it's going to be a plus here. Okay. So we have this over here, and I don't need to write the plus sign there. Okay. So we have this like this now, and now we want to find f of negative 1, right? Because we need f of x, but x is negative 1. So I'm going to take whatever's in parentheses, and I'm going to square it. So it's going to be minus 1 squared times a negative 1 plus 2 is going to equal to 3. Okay. Okay, so we have that, and now what we do is we're just going to plug it into this formula up here, and we're going to have f of x plus h, or I'm sorry, f of negative 1 plus h, minus f of negative 1 divided by h is going to equal 1 plus 2h minus h squared plus 2 divided by h. And then what we can do is we can simplify this. This is going to be equal to, let's see, 2 and 1 is 3 plus 2h minus h squared all over h. And okay, let's see, made a mistake here somewhere. So let's see, minus 1. So if we square, okay, so just let me check, I have a mistake here. So negative 1 squared is going to be a 1, and so that becomes a positive 1. And it'll be 2 times, okay, it'd be minus 2, so it'll be a plus 2. And that becomes a minus 8 squared plus 2. And let's see, f of negative 1 is going to be negative 1 squared is 1 plus 2 is 3. And, okay, so, oh, I forgot to subtract 3. Here we go. I forgot to subtract f of x, which is 3. Okay, so, all right, so we have this over here. Any questions so far? Yes? Mm-hmm. Uh-huh. Where are you looking over here? Which line? This over here? Well, if you... Right here? If you square negative 1, right? If you square the first term, that becomes a 1. And then there's a negative over here. Oh, did I make a mistake? Let's see. Negative 1's, okay. Negative 1 squared is 1 times a negative 1. Oh, that is a negative 1. And then the term in the middle would be minus 2h. That's a positive 2h. That's right. And then that's h squared. And then plus 2 at the end, but this would be a minus 1. Okay. And so this would be a 1. Okay, so this over, okay. Yeah. Here, I'll just start this one over. Sorry about that. It's hard to correct on the paper. Okay. All right. So as we have before, f of x is equal to negative x squared plus 2, right? And x is equal to negative 1. All right. So then what we have here is we want to know what f of x plus h is. Well, f of x plus h is, or I'm sorry, negative 1 plus h is going to equal to negative 1 plus h quantity squared plus 2. Oh, negative. There we go. Thank you. And so this is going to be equal to negative 1 squared is 1, so it's going to be minus 1. And it's going to be plus 2h. And it's going to be minus h squared plus 2. And this is going to be equal to 2h minus h squared plus 1. Okay? Any questions on that? Sorry about the, yeah? So it's a positive 2 and a negative 1, which is going to give you a 1. It's like if you have $2 in the bank and you spend $1. Positive and a negative is going to be 1. So next what we want is we want f of negative 1. And f of negative 1 is just going to be, we take the term, the negative 1, we're going to square it. We're going to multiply by a negative 1 and add 2. Well, negative 1 squared is 1, and times, so this is going to equal to negative 1 plus 2 is equal to 1. Okay? So, any questions on these so far? Okay. So, we have the limit as h goes to 0 of f of negative 1 plus h minus f of negative 1 divided by h. Let me move this onto another sheet. Well, this is going to be equal to f of x plus h is given right here. So this is going to be equal to the limit as h goes to 0 of 2h minus h squared plus 1. And then I do minus f of negative 1, so that's going to be minus 1 divided by h. And this is just going to equal, the 1's cancel out, so it's going to be the limit as h goes to 0 of 2h minus h squared divided by h. Okay? Which one? Over here? Because f of negative 1 is 1, so we're subtracting, so we're doing a minus a positive 1, which gives us a negative 1. Okay? Any other questions? Okay, so we wind up with this over here, and we can factor out an h, so this is going to equal the limit as h goes to 0 of h times 2 minus h divided by h. And the h's are going to cancel out, so this is going to be equal to the limit as h goes to 0 of 2 minus h. And if we let h go to 0, this is just going to equal 2. If we just keep letting h get smaller and smaller and smaller, eventually we're just 2. And we're going to talk about more about that today, actually, is our goal. But did anyone try this one at home? Were you able to try it? No? Okay, well, you have it on here and it'll have on video, but just the basic steps again is you start with the function, and in this case, x is negative 1, so you find out what f of negative 1 plus h is. Negative 1 plus h squared times negative 1 plus 2, because that's the function definition. We found it's equal to this. F of negative 1, well, according to the function definition, we square negative 1, multiply by negative 1 and add 2, because that's what's in parentheses, and we found that was equal to 1. Then we take this term, put it here, this term, put it here, and the rest is just cancel the 1s, factor out the h, cancel the h, let 2 go to 0, and we're left with this. If you use the power rule, then you see right away that we have a nice formula. Using the power rule, we bring the 2 down, the derivative of a constant is 0, so you wind up with the derivative formula is negative 2x. If you plug in a negative 1 there, you get that the derivative is 2. Okay? So, do more of that stuff today, but when you have a nice shortcut or a formula, it really helps you. It's a lot less complicated, like the power rule. When you don't, when you have nothing to work with, you're trying to take the derivative of some new function you've never seen before, or I've never seen before, there are no rules for it, then you always have to go back to this definition. Most of what we'll do in this class will not be with the definition just for the first chapter, but you still have to know it. It's going to be with special formulas and special rules, okay? For the cases we'll handle. All right, so let's go back to the PowerPoint. And, okay. All right, so now we're going to talk about limits in the derivative, and we're going to talk about continuity. All right? So, limits in the derivative. Now, the idea of the limit, like we saw in the last section, we were letting h go to 0. Okay? That's what a limit is. We're letting some number or variable not equal something, just get close to it. Okay? Like in the last example, we said let h go to 0. We found the derivative was 2. So it has an intuitive idea to it, but the intuition doesn't always work because we wind up with all these cases that we don't know how to handle just by plugging in 0 for h or something like that. So we have a theory behind it, and there are limits. Okay? So the idea of a limit, we say if a variable is x, and we let x approach a, what is our function approaching? All right, that's the whole idea. That's what the definition up here is saying. And that's what we did in the last example. We said, as h goes to 0, what is this function getting closer and closer to? Well, that equation we had up there is getting closer and closer to the derivative. But we don't have to talk about derivatives. A limit is any time we have x approach some number. Let's look at something a lot simpler than we did in the last section. Let's look at x cubed minus 7 and let x approach 4. All right? Now, a limit has to be unique, so it means if we approach it from a number bigger than 4 or a number less than 4, it has to be the same number. And you probably would guess, just like we plugged in 0 for h in the previous example, if x is going to 4, we can just plug in 4 here, and that's exactly what it does. If we plug in 4.1 for x, if we plug 4.1 in for x into this expression, x cubed minus 7, we get 61.92. If we get something a little smaller, we get 57.481. If we plug in 4.001 into x cubed minus 7, we get 57.048. And as we get closer and closer, it's getting closer and closer to 57. Well, if I plug x equals 4 into this equation, what do I get? 57, right? 4 times 4 is 16. 16 times 4 is 64. 64 minus 4 is 60, minus another 3 is 57, right? So 64 minus 7 is 57. Right? So start with numbers less than 4. If we plug in a 3.9 for x, we get this number here. If we plug in a 3.99 for x, we get 56.521. If we plug in a 3.999 for x, we get 56.952. and we plug in a 3.9999, we get 56.995. So we're getting closer and closer. The idea, it doesn't matter if we approach from numbers from the left, which is below 4, or from the right, which is numbers above 4. We get closer and closer. As x goes to 4, the limit gets closer and closer to 57, which is if we just plugged in a 4 for x. So 4 cubed minus 7 is 57. Okay. Here's a graphical example. Illustrates the same idea. The blue is some function. The little circled dot here means the function is not defined there. There's no value of the function when x is 3. And that happens a lot. We have a function that's not defined somewhere, but we want to know as the function is going towards this number, what's it getting closer to? Okay? So that's a common example where you just can't plug in a value like we did before. So as we approach 3 from the left-hand side, the function is getting closer and closer to what value on the y-axis? 2. As we approach 3 from the right-hand side, we'll follow the function in that direction, the blue line. What is the function value getting closer and closer? Well, as we approach 3 from above, that's the x-axis, what is the function value on the y-axis getting closer to? 2, right? The function values are over here, the x value is over here. So as the limit, as x goes to 3 from the right-hand side, the function is going to 2. As x approaches 3 from the left-hand side, this way, the function is still going to 2. So the limit exists here, and the limit as x approaches 3, where the function is 2. The function doesn't have a value at 3, but as we get closer and closer to 3, the function is getting closer and closer to 2. Okay? All right. Now, this is kind of your memorize slide. I think it's best not to memorize, just practice problems and get used to using these. These are the rules for limits. Okay? It's a big list, but they're very intuitive, and you've already used some of them. If the limits exist separately, you can take the limits separately. Like, if you have x squared plus 7 as x goes to 0, the limit as x goes to 0 for 7 is going to be 7. The limit as x goes to 0 for x squared is going to be 0. So you can split limits over addition. We're going to do some examples. You can split limits over subtraction as long as both the individual limits exist. You can split limits under multiplication as long as both limits exist. You can pretty much do whatever you want almost. There are exceptions, but almost with limits are very nicely behaved. Derivatives, when we get to derivatives, they're more complicated. But when we're just talking about limits, almost anything goes. Not everything, but almost anything goes. If you're taking the limit of one function divided by another function, if both limits exist and the bottom limit doesn't go to 0, you can just take the limits separately. The one I didn't mention is the one up here, where if you have a function raised to a power, you can just take the limit of the function inside the power. And we'll do examples of these. You can also pull out constants. Okay? So we're going to do an example, and this example works through a lot of our properties. And just looking at this, I can already tell I can just plug in 9 for x, and that's going to be my answer. We're going to see why that is, but limits are very nicely behaved. In most cases, they're not very difficult to do. The derivatives you'll have to memorize those rules, but these should be pretty intuitive. Okay, so let's take a look at this. We're going to do x squared minus 5x minus 36 divided by 8 minus 3x. So we're going to have the limit as x goes to 9 of the square root of x squared minus 5x minus 36. And it's going to be divided by 8 minus 3x. Okay? Now, normally you're not going to go through all the steps I'm going to go through because you'll just be able to see it more easily. Now, the first thing I'm going to note is a square root is a 1/2 power, so I can bring limits inside square roots. All right? So this is going to be equal to the limit as x approaches 9 of x squared minus 5x minus 36 raised to the 1/2 divided by 8 minus 3x. Remember, a square root means raised to the 1/2 power. Well, I can always, when I have something raised to a constant, I can bring the limit inside. And I can also split a limit over division when the bottom one doesn't go to 0. Well, 8x minus 3, I can just plug in 9 for that, and that's not 0. So this is going to be equal to the limit as x goes to 9 of x squared minus 5x minus 36 all raised to the 1/2 divided by the limit as x goes to 9 of 8 minus 3x. Okay? And one of my rules is I can break limits over addition and subtraction. So I'm just going through these steps kind of tediously. You might be able to see that you can just plug 9 in for x and be done, because I can split the limits over addition and subtraction. So I can take the limit of x squared minus 5x and minus 36x separately, do the same thing for the bottom, and I can pull out constants. So that's the basic idea. I'm going to finish that off on the slide, what I was doing. The first thing we did is we can distribute the limit over the quotient. So we can do this. Then what we can do is, because the square root means raised to the 1/2 power, we can bring the limit inside the square root. Because whenever we have a constant, we can bring the limit inside. Then what we can do is we can take the limit of each term separately. I can take the limit of x squared, 5x, and 36 separately. And because it's x squared, I can bring the limit inside again to get this. For the 5x, I can pull out the constant. So I have 5 times the limit of x as x goes to 9. I do the same process on bottom. And, well, as x goes to 9, this is going to 9 squared. And this is going to negative 5 times 9. The limit of a constant is just going to be a constant. There's no x to vary. And we plug in the 9s, we solve, we're done. Okay, so basically you could have just plugged in 9 from the very beginning. This is, yes? Does that work for a limit? We're gonna look at the cases that it works for right now and distinguish for the ones it doesn't. Okay. The most popular type of function you're going to have here is a polynomial. A polynomial just means something of the form x squared. You have powers of x added together. So everyone here should know what a polynomial is. You're just adding powers of x. If you have a polynomial, you can just take what the limit is going to and plug that in for x. You're done. If you have a rational function, which means one polynomial divided by another polynomial, everyone should be familiar with that, and in the bottom polynomial, the one you're dividing by, if you plug in the value for x that you're approaching and it's not 0, then you can just plug it in and you're done. Okay? So limits are usually very nicely behaved. Generally, you can just plug in the value for x because they split over multiplication, they split over addition, You can factor out constants. You can put them in powers. So generally, you're safe just to plug in the value. Now, there are cases where you can't do that. For instance, we'll do some examples of that. I'll do an example right now to illustrate where you couldn't do it. Suppose we have the limit as x approaches 1 of x plus 1 times x minus 1 divided by x minus 1. Okay, this is a rational function. And look at the bottom. As x goes to 1, what does the denominator go to? 0. So we can't use our theorem. We can't just plug in here. It turns out we can actually just cancel these out and look at this is equal to the limit as x goes to 1 of x plus 1, which is going to be what? 0, right? Okay. So, but if you have a polynomial, just plug in the value you're approaching for x. If you have a rational function and the denominator, which I have right here, is not going to 0, you can just plug in x. Okay? Or if you, and also, whenever you have, let me do one more example like that. Whenever you have a root, let me do one more example. Whenever you have a root like something like this, say we take the limit as x goes to 2. Whenever you have a root of something, you can just plug it in also. Okay? You want to find out what this is approaching, and this is just one of the properties from the sheet, because like I did in the example, I just want to pound it in, illustrate it again. This is equal to limit as x goes to 2 of x squared plus 1 raised to the 1/2. And whenever you have something raised to a power, you can bring this limit inside. So what you can do here is when you have a square root, you can just move the limit inside the square root. Okay, and then work with it. And since that's a polynomial, you can just plug it in. But you'll get some more practice with that. All right, compute the following limit. Okay, we just did this one. Okay. Use limits to calculate a derivative. Now, I already did one of these at the beginning, so I did this part first, but try this one at home, and I'm going to post a video solution for it. I don't want to do it here since I already did one. But copy this one, try it out, and see if you can get the answer right, and I'm going to post a solution for this one, okay? But remember, you're just using the definition of the derivative. The limit as h goes to 0 of f of 3 plus h minus f of 3 over h, because you're evaluating the derivative at 3, okay? Okay, so this is our last example for this section, and we want to talk about one last concept with limits, and we're going to start talking about continuity. Sometimes it makes sense to say let x go to infinity, right? What is the function doing as x is getting arbitrarily large negative number or an arbitrarily large in magnitude negative number, right? To say x is going to infinity. Well, we're going to have a trick, and what we're going to do for the trick, but I want to show you guys something first, is we're going to take the term with the x value with the largest power, which in this case is x squared, and we're going to divide everything in the numerator and the denominator by x squared. So just a little trick. In mathematics, sometimes you have to have your bag of tricks in order to get through some problems, learning from what other people have figured out. And it's a trick that commonly works, but we're going to note something first. Whenever we have the limit as x goes to infinity of 1 over x, this is equal to 0, right? 1 divided by 2 is a half. 1 divided by 4 is a fourth. 1 divided by 100 is even smaller. 1 divided by 1,000 is even smaller. 1 divided by 1,000,000 is extremely tiny. 1 divided by 1,000,000,000. So as x keeps getting larger and larger and larger, 1 divided by that really huge number, like if you can think of taking like a pizza or something, divide it between 1,000,000 people, right? Each person's getting approximately 0 slices of pizza. Then divide the one pizza into 1,000,000,000,000 people. It's impossible. You can't even do it. I mean, they're getting dust at that point, right? Okay, so whenever you take something and you divide it, as you let x go to infinity, 1 is being divided by a larger and larger and a larger and a larger and a larger number. So the limit as x goes to infinity of 1 over x we're defining to be 0. Okay? And we're doing that because it makes sense. If you just let x keep getting bigger and bigger and bigger, 1 divided by x keeps getting closer and closer and closer to 0. All right? And we need that for this problem. Okay. So we want to find out, now the problem is, if we take the limit of the numerator, what is the numerator going to? It's going to infinity, right? And we take the limit of the denominator, that's going to infinity. 10 times x plus 100. If we let x keep getting bigger and bigger and bigger, 10x plus 100 keeps getting bigger and bigger. So that's going to infinity. And if we have x squared minus 30, as x squared minus 30, as x gets bigger and bigger and bigger, x squared gets bigger and bigger and bigger. And this bottom here is also going to infinity. So what we're going to do here is we're going to divide everything by x squared. And it's just a trick. All right? Sometimes in mathematics you just have to try things to see what works. This is a very common one. So what we're doing here is we're dividing everything by x squared. Then what we can do is we can just take the limits. We can just take the limit of the numerator and the denominator separately. Eventually, we can just plug in an infinity for x, essentially. And 10 over x, that gives us a limit of 0. 10 divided by infinity is going to be 0. 100 divided by x squared, as x goes to infinity, is going to be 0. Or you can think of it like 100 divided by the largest number possible. That's going to be 0. The bottom, that's just a 1. 30 divided by x squared, let x go to infinity, that's going to be 0. And 0 divided by 1 is going to be 0. Okay? Okay. So let's look at that one again. So I'm just going to take the limit as x goes to infinity of 10x plus 100 divided by x squared minus 30. Okay? So let's rewind that and just go through that again. So if we divide, what we're going to do here is if we look at the numerator is the limit as x goes to infinity of 10x plus 100. Now if I plug in infinity for x, what would be 10 times infinity plus 100? It'd just be infinity. If you can't have anything bigger than infinity. Right, we're adding an extra concept here, right? Think of infinity as kind of like the largest number possible. It's not really a number, but if we multiply 10 times the largest number you can think of, you still have the largest number you can think of, and if you add 100, it's still nothing bigger. It's still infinity. All right? And if we take the limit of the bottom, which is x squared minus 30, right? As x goes to infinity, what should x squared go to? Infinity. Is subtracting 30 going to change anything? No. Because you just keep making this bigger and bigger and bigger. You're not slowing it down, right? So infinity is not really a number, but it has properties like a number. If you add anything to infinity, you still get infinity. If you subtract any number from infinity, you still have infinity, right? So if you take any number and divide it by infinity, you get 0, right? So it has properties, and this over here is going to be infinity, all right? Whenever we have infinity in the numerator and infinity in the denominator, we can't plug in x like that. So that's why we're using the trick in this example. So the trick we're going to use in this example, whenever you see this, this is the trick you want to try out, is we have the limit, I'm just going to rewrite the problem, as x goes to infinity of 10x plus 100 divided by x squared minus 30. Now, what I'm going to do is I'm going to look in the numerator and denominator, and I'm going to find the x value with the highest power. What term is that? What is it? X squared. So I'm going to divide every term in the numerator and the denominator by x squared. So I'm going to rewrite this. As long as I divide the numerator and the denominator by the same thing, it doesn't change anything. So this is going to be the limit as x goes to infinity of 10x divided by x squared plus 100 divided by x squared all over x squared divided by x squared is just 1, and this is going to be minus 30 divided by x squared. So I just divided every single term by x squared. Now, this 2 is going to cancel with this x, which is 10 over x. Now, as I let x go to infinity, what is 10 over x going to? What? 0. So this term is going to 0. As I let x go to infinity, what is 100 over x squared going to? 0. 1 is just 1. As x squared goes to infinity, what is 30 over x squared going to? 0. So this is going to equal 0 plus 0, because remember, I can split limits over addition and division, and subtraction. So this is going to be 0 plus 0 divided by 1 minus 0. Okay? Now, you're going to have to do a few of those to get used to it, but the idea is infinity is not a number, but it has properties like a number. You take anything and you divide it by an ever-increasing number, it's getting closer to 0. Add anything, it's not going to add another number, it's not going to change it. Subtract another number, you can't change it. The only problems you run into is when you have infinity divided by infinity and infinity minus infinity. Then you have to rearrange your equation like we did in this example. If you come up with infinity minus infinity or infinity divided by infinity, then you have to rework your equation to get something different. Like in this example, what we did is we divided everything by x squared, and that changed it enough, the equation enough, that we could just plug in infinity and it works. But you can't have infinity divided by infinity. Your theorems don't work for that. And you can't do infinity minus infinity. Your theorems don't work for that. Okay? All right, so let's go back to the slide here, and they do the same thing. They divide everything by x squared. Then, as x goes to infinity, 10 and 100 divided by infinity give us 0. Okay, now we're looking at differentiability and continuity. And for differentiable and continuity, this is a short section. It's just it's a slight extension on the limit concept. We're going to add one more criteria for on a limit, and that's going to give us what continuity is. And what we're going to look at here, differentiability, non-differentiability. Graphs, non-differentiable at a point, continuous, discontinuous functions. So continuous is really, really important in math, right? We don't like things that jump around a lot. For people who study finance, they get into an area of calculus called stochastic calculus. Sometimes they work with jump processes where you could be at one point, say at one price or something, then it jumps up to something else. It's not a continuous, smooth movement. So they deal with those cases. But for these cases, but when things are continuous, it really helps us out a lot. All right. So these are examples of non-differentiable. The first one we've looked at before. Whenever we have a sharp corner, it is not the function is not differentiable at that sharp corner. It might be differentiable everywhere else, but it's not differentiable at the sharp corner because whenever we have two lines intersect, the derivative of the line is the slope of the line. Well, this line has a positive slope right here. This line has a negative slope right here. So what should be the derivative of the point where they both intersect? Well, we don't know, right? This line, say, has a slope of positive 1. This line has a slope of negative 1. A is in the middle. The slope is the derivative of a line. So we don't know what this guy in the middle should be. The same process winds up over here. Whenever you have a big cusp like this, you have a similar problem. And it's not going to be differentiable at this point. The tangent line is actually going to be straight up and down. Here we have another sharp corner example. Can't have that, even if it's not straight lines. And over here, we have the tangent line is vertical here. So in this example, and let me just draw that last one out. So remember, the tangent line is how we approximate a curve. So look at this function over here. It's actually not a function. Okay? Now, if we look back to 1.2, and we try and draw a tangent line, the tangent line at that point is going to just be, if I try to draw it just by approximating, it will look something like that. If I try to draw the tangent line, not using the derivative formulas and everything, just try to look at the graph and guess it, and I try to look at, say, this point over here, the tangent line would look something like that. But what about at this point over here? Okay? If I try to draw the tangent line at this point over here, it's straight up and down. All right? So the derivative is undefined at that point because it's a vertical line. Vertical lines are not even functions. So if we go back to our chart here, this case is a sharp corner. Derivatives cannot occur at sharp corners. This case is another sharp corner. Derivatives cannot occur at sharp corners. You cannot have the tangent line be a vertical line. So if your tangent line at the point, like over here, and this is also a sharp corner too, you cannot have the derivative at this point. And over here is another example where your tangent line is a vertical line. Like I just did, you cannot have a derivative there. So you should be able to look at a graph and look at a point on a graph and say, is the function differentiable there or is it not? Okay? Here's an example of something where you have a non-differentiable function. And that's taxes based on your tax rates. Okay? So on your earnings for the first $27,050, you have a 15% tax rate. So on that first $27,050, I'm sure you guys know more about the tax system than I do, but according to this chart here, for the first $27,050, you're paying, the percent of your money you're paying back to the government is 15%. But starting from for your earnings over $27,000 and up to $56,000, you're paying at a different rate. And once you're above this number over here and up to this number here, you start paying on those earnings from above 136 to 297. You're paying 35.5% rate, and so on. So once you hit each of these, the rate that you're paying money to the government back is jumping. So the derivative is changing, so you don't have straight lines anymore, you have sharp corners. So I'm not going to go through the derivation of the formula, but I want to point out what the graph looks like. So this is just a function that they come up with, and if you guys would like, I'll post a video on it if you want to see the derivation, where this function comes from. But look, what's the rate of change? So this is a piecewise function. Look at the first line here, 0.15x. What is the rate of change of that line? What? 0.15, right? Now, for the second tax bracket, the tax rate was 27.5. So for the second line here, if you simplified it, what should be the slope of the line for that point? 0.275. If you simplified this out, you'd wind up with the slope as 0.275. And if we look at the third line, we would have, if we look for all your earnings between 136 and 297, you would have yet another another rate that you're paying back to the government of 35.5%. So each time you hit a change in your tax bracket, the slope of the line is increasing. Since they're straight lines, every time it increases, you wind up with a sharp corner. Sharp corners are not differentiable because the point at the corner, you're not sure at that particular value what point what should be the rate of change at that particular point. Okay? Okay. All right. And if we were to draw this, I'll just draw it on paper because it's kind of hard to see. So, so we start out with a line that starts at 0, and it goes to around 27,000, I think. 27,050 was it? Right? And we wind up with a line, and the slope of that line is 0.15. And we get this. Now, right after you hit this number, and I'm going to exaggerate the slope so you guys can see it, is going to go up like this. Right? From 27 on, you wind up with a line with a new slope. And I exaggerated the increase of the slope here so it was easier to see, but you have, on this slope line over here, you have a slope of 0.27. On this line over here, you have a slope of 0.15. And this point over here is on both lines. It's making a sharp corner. So you're not sure if this point should have a rate of 0.15 or a rate of 0.27. Now, you know, the Internal Revenue Service, you know, they tell you what it should be, but mathematically it falls on both lines. So for that one point, well, which rate should it fall under? Because it's on both lines for the function. So according to this, it could go either way. And of course, the Internal Revenue Service, they can say, well, it's this way. But mathematically, it could be either way, and it would make sense. Okay? So, okay. So we come back to the slide, and the idea is whenever we have something with sharp corners, it's not going to be differentiable at the point where it changes. Okay? Now, over here we have a now now we're going to look at something what we call continuous functions, all right? We talked about differentiable. Now we're going to talk about what it means to be continuous. A function f is continuous at x equals a, provided that, roughly speaking, its graph has no breaks, no gaps, as it passes through the point a comma f of a. That is, f of x is continuous at x equals a, provided that we can draw the graph through a comma f of a without lifting the paper from the pencil. Okay, so the idea of a continuous function, and this is really important in mathematics, it helps us a lot. In finance, Dr. Long in the math department, he studies this stuff. Unfortunately, a lot of times in finance, stuff jumps around a lot, so it makes the math a bit more complicated. But we're going to look at cases in this class where the continuous things do apply, and it's quite a substantial amount of stuff. The idea of the continuous function is you can basically trace the function with a pencil or your finger without lifting your pen. Or your pencil. So this function is not going to be continuous because when we get to 3, there's a break here. So we have to pick our finger off the function and continue on the other side. So this function is not continuous at 3. Notice the limit exists at 3 because as we approach 3 from the left, and we approach 3 from, as we approach 3 from the left-hand side, the function is getting closer to 2. As we approach 3 from the right-hand side, the function is still getting closer and closer to 2, but it's not continuous there. Because the value, if it was continuous, it would have to be 2, but it's not even defined at all. Okay, here's a theorem. If f is differentiable at x equals a, or a point a, then f is continuous. So if a function is differentiable at a point, it's continuous at a point, but not the other way around, right? A function can be continuous at a point, but not differentiable. But if you're differentiable there, you have to be continuous. Differentiability is stronger than continuity. Differentiability implies continuity, but not the other way around. All right. So just remember, differentiability is like king. So when it comes to studying smooth functions, we call them, differentiability is like at the top of the chart. It pretty much implies everything else. So if you have differentiability, you have the properties of pretty much anything else you can think of. Not totally true, but it's very, very strong assumption when you have differentiability. Okay? Continuity is very weak assumption. Lots of functions are continuous. A whole lot more functions are continuous than differentiable. Okay? So there are many, many, many continuous functions, not so many differentiable functions. Differentiability implies continuity, not the other way around. So what is continuity? We have a graphical idea of it. Here's how we find out if a function is continuous. All right? Well, if it's continuous at a point a, the function is defined at a, so we compute f of a. Then we compute the limit as x goes to a. And if the limit as x goes to a and f of a are both the same number, then it's continuous at that point. Okay? Or the value of the function at that point should be what it's getting closer and closer and closer to as we get closer to that point. It shouldn't jump somewhere. All right. Thank you. Okay. Determine whether the following function is continuous or differentiable at x equals 1. So first of all, this is a piecewise function. It's broken into 2 lines. What is the slope of the top line? Can someone tell me what the slope of the top line is? What is the slope of the bottom line? 3. So, at the point where this one ends, which is 1, and this one begins, can it be differentiable? What's your slope on top? What's your slope on bottom? What's the derivative of the top line? 1. What's the derivative of the bottom line? 3. The slope of a line is its derivative. Okay? So, according to the top line, the derivative at x equals 1 should be what? What's the slope of the top line? 1. According to the bottom line, the derivative at x equals 1 should be what? 3. So what should be the derivative at 1? Should it be 1 or should it be 3? Anyone take a guess? How many people don't know? I don't know either. That's the problem. It's not differentiable there. Okay? That's the point I was making on the slide about the tax brackets. We have two lines here being pieced together. It's a piecewise function. The slope of the top line is 1. The slope of the bottom line is 3. So where they meet at 1, this one ends at 1, this one starts at 1. Right? 1 is on both lines. Okay? So the derivative of 1 according to the top line is 1. The derivative of 1 according to the bottom line is 3. So which one is it? It's neither. The derivative is not defined. It's a sharp corner. If we graph this guy, we have x equals 2 and 3x. Let me draw this for you again. If we draw this guy, we have x equals 2, so our slope-intercept is 2. So we have, sorry, can you hear? Okay, so we, right? So let me tab over here. So if this is 2, so this is the line x plus 2. And say this is the line 3x, right? It's just, we're starting a little bit later on. So notice the sharp corner here at 1, this is where they meet. 1 falls on both lines. So the piecewise function says take x plus 2 from 0 to 1, then continue with the line 3x. Well, 1 is on both lines. So the derivative at 1 could be the slope of this line, which is 3. Or the derivative at 1 could be the slope at this line, which is 1. Alright, so the idea here is when we look at this piecewise function, first we're going to ask, is it differentiable at x equals 1? So what's the answer? So whenever you have a sharp corner, is it differentiable? No. Do you have a sharp corner here? Is this function differentiable at 1? No. Right? Why? Specifically, sharp corner, that's good enough. But the reason sharp corners don't work is, well, look at here. You have a slope of 1 here. You have a slope of 3 here. The slope is the derivative. But this is on both lines, so you're telling me this has a derivative of both 1 and a derivative of 3. That's not possible. Okay? So it's not differentiable there. Okay? So it's not differentiable. We want to know, is it continuous? Okay? We want to know, is it continuous at x equals 1? Okay, so let's look at that problem. We want to know, is it continuous at x equals 1? So we're going to have the limit, and I'll switch over there in a second, as x approaches 1 of f of x from the left-hand side. Okay. Now, if we're on the left-hand side of 1, what is the function equal to? So if we're less than 1, what is the function equal to? Or if we're less than 1 and greater than negative 1? X plus 2. Right? So this over here is going to be equal to the limit as x approaches 1 from the left of x plus 2. And that's just a polynomial, x plus 2, so we can just plug in -1. So this becomes 3. That negative up there is not -1. When you see it up there with the limit, it means you're going to x from the left. Now the limit, as we approach x from, or 1 from the right-hand side of f of x, is going to be equal to, if we go back to our chart, if we're bigger than 1, and we're approaching 1 from bigger than 1, what is f of x equal? So if x is bigger than 1, what is f of x? 3x, right? So if we're approaching 1 from bigger than 1, we're going to use the bottom one, which is 3x. So this is going to be equal to the limit as x approaches 1 from the right, which is going to be equal to 3x. And that's a polynomial, so we can just plug in the 1 and we get 3. So that means the limit, since if we approach from the left we get 3, if we approach from the right we get 3, then the limit as x goes to 1 of f of x equals 3. The limit exists because it doesn't matter if we go from the left or the right. Now, the other thing we have to know is what f of 1 equals. So remember, to find out if it's continuous, first we find what the limit is. Well, the limit is 3. Then we find out what the value of the function is at that point. So if we go back to our example here, if x equals 1, then we're on the top graph, right? Then we're on the top graph, and if we plug in 1 over here, what do we get? 3. So f of 1 is 3. So f of 1 equals 3. So the function is continuous at 1, right? Because we need two conditions. Because we need the limit exists equals 3, and the value of the function at the point also equals 3, and they're both equal. So we say the function is continuous at 1. All right? Why? Because the limit as x goes to 1 of f of x is equal to 3, and the limit as x goes to 1, and the value of the function at 1 is also 3. Since these guys are equal, the function is continuous at 3. Okay? So if we go back to our side, remember, the function must be defined at a, the limit must exist, and both the limit and the function value must be equal. Okay, and that's exactly what they do here. Okay. All right. Okay. So that brings us into section 1.6. Now, I'm not going to do 1.6 on the exam. I'm going to give you guys a quiz on that afterwards, but I am going to start 1.6. And you will have a quiz on 1.6, but it won't be before the exam. Okay? So, some rules on differentiation. Okay? So rules on differentiation, they're a little bit more involved than taking limits, right? Remember, differentiation is a special type of limit. We can still pull out constants, that's great. We can still separate it over addition when both derivatives exist. But when we have something raised to a power, remember we have a special rule for that, the power rule. We bring the constant in front, subtract 1 from the exponent. Now we're going to add another rule called the general power rule. Okay, so just to recap what we've been doing, section 1.1 is on lines and slopes of lines. Section 1.2 is an intuitive idea of the slope of a curve by drawing lines on the curve. We call them tangent lines. 1.3 is we talk about the general idea of the derivative and then the equation for the tangent line. Then we give a formal definition for the derivative in terms of limits. We expand that on 1.4, and we go back to the derivative definition of the limit. And now we're going to learn how to take more complicated derivatives. So everything so far has just been about derivatives. Now, derivatives have, these are the three rules we're adding for this section that we're going to go over, and this is the majority of the section. One is we can pull out constants, one is we can separate over sums, and one is we can bring down powers, okay? Sure. So this is a slide you want to memorize, okay? We're going to do examples, and sometimes memory doesn't help. Just doing examples and using the properties over and over, you get an idea with it. Sometimes the actual rules when you're reading math, before you do some examples, don't make a lot of sense. If you send me an email, I'm also happy to post the slides. If you would like the slides, I'm happy to post them on Blackboard. Okay, move on. Okay, I'll give 2 more minutes to copy them, then I'll move. Okay. I'm going to go on, but I will post them. Just someone send me an email to remind me, and I'll post them right after class. Okay. So differentiation. So we're going to basically use some of our rules to differentiate this guy. First, I'm going to do it on here. Then I'm going to do it on paper, just for some reinforcement. We're going to use the general power rule for this, in the fact that we can take derivatives separately over sums. First thing we're going to do is we're going to rewrite this fraction as a polynomial raised to a negative power. Okay, so the first thing we do is 1 over x cubed plus x plus 1 is the same as x cubed plus x plus 1 raised to the negative 1. Right? Whenever you have something in the numerator, you can bring it up top and give it a negative exponent. Now what we're going to do is we're going to use the generalized power rule. So we're going to bring the negative 1 in front, and I'm going to do this on paper also. We're going to subtract 1 from the exponent. All right? And then the generalized power rule says we multiply by the derivative of the inside. Okay? Now, this is, okay, so we wind up with this case, and that's it. Okay? All right. So, I only have 5 minutes left, so what I'll do is I'm going to work this one out on paper, and I'll post a video for this one and the other one. There is one thing before you go. I want to talk about the test real quick and the quiz. For your first quiz, and you can only do this if you're here in class, now is it's very easy, and this was my the proctor's suggestion, and this is just for the first quiz to get people to go to the math lab. If you're in class now, I'm going to just pass around an assignment sheet, and you take this to the math lab. I'm sorry, if you go to the math lab, you can do a 10-minute session there. You'll get a free 100 for your first quiz. Not free, you guys have to go there. This is just for the first quiz, and it's something Course Corner thought of. So if you just pass this around, and I'll get 2 sheets going so it doesn't, so it goes quicker. So if your name's on this sheet, you go there for a 10-minute session, and I'm going to hand out sheets where you, I'm going to email out a paper, you can get it signed on. You'll get 100 for your first quiz, so that'll be good. If you haven't signed up on the sheet, then you don't get the offer. Yeah?